Hey, what's up, guys? My name is Saurav, and this is my YouTube channel, Data Science Novice. So, if you are new to my YouTube channel, please do like and subscribe. Your efforts are massively appreciated. So, in the last video, we talked about CNNs, that how it works, and then we built image classifier using Tensorflow. So, in this video, we will see that how can we improve the model, and we will learn about batch normalization and data augmentation techniques that helps in improving the model accuracy. And in later part of the video, we will implement these techniques using TensorFlow. So what is batch normalization? So a batch normalization normalize each input channel across a mini batch. And this is also known as internal covariate shift. This has effect of stabilizing the learning process and dramatically reducing the number of training epochs required to train the deep networks. So here's the example of simple neural network. Remember from the previous video, before feeding the data to input layer, we normalize it. So here we normalize the data only once. But what happens when data is passed from one layer to another? It becomes non-normalized, and that keeps on happening from one layer to another layer. So why this is a problem? So one potential problem is that the distribution of the input to layers somewhere down in the network may change after each mini batch when the weights are refreshed. This can make the learning algorithm always pursue a moving target. To deal with this problem, what we do, we add another layer, that is batch normalization layer, in between two layers. So this way each layer gets the normalized data from the previous layer. So here is the formula used. And if you are coming from stats background, you might have guessed that we are calculating Z score here. And this gives us value ranging between -3 to 3. So mu is the batch mean and sigma is the batch standard deviation. But how do we know that this scaling is good? And the answer is no, we don't know whether it is good or not. Because here we are deciding the normalization for the network and not the network itself. So what we do, we introduce another equation. So here gamma and beta are learned parameters. So network decide the value of these parameters during the training process. So let's look at a very simplified example. So here we pass normalized data to dense layer. Next, it outputs these number and we can see that these number are ranging between -64 to 90. This data then passed to the batch normalization layer where it converts the value in range between -3 to 3 using z-score formula. Next, we modify these values using the equation where gamma and beta are decided by the network. So this is all from my side on batch normalization. If you want to know more about this, there is original paper available on Google. Next, we are going to talk about data augmentation. So data augmentation is the technique of increasing the size of data used for training a model. For reliable prediction, the deep learning model is often require lots of training data, which is not always available. The intent is to expand the training dataset with new plausible example. This means variation of training set image that are likely to be seen by a model. For example, a horizontal flip of a picture of a cat may make sense because the photo could have been taken from left or right. Also, we can change the color composition of the same image and that can deal with the problem of different lighting conditions. So some of the most common data augmentation technique used for images are positional augmentation and color augmentation. So let's look one by one. So the positional augmentation is related to the position of an image. So here we have original photo of the dog and on the right hand side we have a photo of the same dog rotated 45 degree. Next we can pad the image and it helps in increasing the size of the image. We can also reduce the size of the image by applying scaling. And lastly we can flip the image. So these are some of the positional augmentation we can apply on images. Next we have color augmentation. So in color augmentation we try to play around with color composition like increasing the brightness, changing the color contrast and so on and so forth. So you see, although all these images look same to us, but that is not the case with CNNs. So with the help of data augmentation, we are able to generate 8 images. So this way augmentation helps in generalizing the model. So that's all from my side. Now let's see the implementation in Google Colab. So here I am in the Google Colab and I have already written the code. Since all the code is going to be same, so we just going to add some extra lines and you can always find the code on my GitHub account. So first we have imported all the necessary libraries and the extra thing we added is batch normalization layer and image data generator for the data augmentation. We are going to use the same dataset So this time we won't be investing our time in data visualization because we have done this in previous video. Another thing is using same dataset will allow us to compare the result, that whether we have improved the model or not. Next we import CFAR10 dataset and we normalize it by dividing each pixel value with 255. So this way we get a data containing value ranges between 0 to 1. And why we do that? So that our neural network train faster. So next we build the model. So far you must have realized that neural networks is like Legos. You have pieces of plastic and by combining them, you can make anything. Similarly, here we combine layers and we try different configuration to get the result. Here I have used one such configuration. And note that I have tried many other combination before reaching this result. So one of the first step to improve the model is to try different number of layers. So let's talk about this configuration. So here first we use convolutional layer which has 32 filter and then we added another parameter called padding and the link for that is in the description. Next we have kernel size. So in this layer we just added a new parameter and everything else is same as in the previous video. Next we add batch normalization or batch norm layer that we learned in the beginning. So this will scale down the input coming from convolutional layer. And next we add our activation layer. And then again we have this con layer with 32 filters. So basically we have repeated the whole thing. And additionally we have added pooling layer. So to make network easy to understand, we call this whole thing as a block number 1. And we have used 4 such blocks in this network. And in each block we have increased the number of filter by the factor of 2. So in the first block we have 32 filters, in the next block we have 64 and so on and so forth. Next, we flatten the layer so that we can connect the output of the CovNet to the fully connected layer to get the final result. And finally, we build fully connected layer, which is very similar to what we built in the previous video. Next, we compile the model and we are going to use Adam Optimizer. Next, we use sparse categorical cross entropy to calculate the losses. And then we decide the metric for the model. Next, we decide the parameter for early stopping. So we are going to monitor the validation loss and when it's minimum, we run the model for 3 more epochs and then we stop the training. Note that I am assuming that you have watched all my previous video because I have already explained these things in great details. Next we check the summary of the model and here we can see that this is by far the most complicated network we have built. And in later videos, we will see some state of the art models that are very complicated or you can say very deep because they contain hundreds of layers or even more. So in total, we have to train 13,73,886 parameters and we have 1,408 parameters that are non-trainable in nature. So what is non-trainable parameters? These are those parameters you cannot optimize their value with your training data. In another word, non-trainable parameter of a models are those that you will not be updating and optimizing during the training and that have to be defined prior or passed as an input. Next, we fit the model to the training data and again everything is same as the previous video. So let's run the model. And training has started and make sure to switch to GPU else it will take a lot of time to train. So training may take some time, so I'm going to fast forward it. So here we see that model stopped training after 8th epoch. That means it compared the 4th and 5th epochs and realized that validation loss increased after the 4th epoch. And from there it trained for 3 more epochs before stopping the training. Next we save the model history and visualize the losses and accuracy of the model. So here we can see that we are getting 79% accuracy, which is 10% more than the model from the previous video. So this way batch normalization help improving the model. So far we only use batch norm in convolutional layer and not in the dense layer. So as a practice you can try adding batch norm in dense layer and see whether you are able to improve the model further or not. Next we are going to train the model on augmented data and see whether we improve the model further or not. So first we create an image data generator instance and we pass few things. That is rotation range 20. So this will rotate the image clockwise or anti-clockwise randomly by angle between 0 to 20. Next we pass the width shift and height shift, which will change the height or width of the image. And lastly we pass horizontal flip equals to true. As the name suggests, this will flip the image upside down. We have experimented with few, But there are many such operations, and if you want to explore more, I would suggest you to check the documentation. So this way we have increased the dataset. Next we fit the image generator on the training data. Next we are going to initialize the same model. Note that if you call model.fit, it will start the training from where it left off. That means we will have previously trained weights with us. So if we want to train the model from the beginning, we have to reinitialize the model. Next, to train the model, we call model.fit, and this time instead of passing training data, we have to call flow method of our data generator object, and we pass training sample and class they belong. So this will start creating the image having different angles or different width or even flipped images. Next, we pass the batch size for this flow method. Next, we pass the steps per epoch, which is nothing but length of data divided by batch size. Then we pass the epochs, and instead of splitting the data, this time we are going to pass the test data as a validation data. So let's run this cell, and you can see that training has started, and this time we have more data than the previous one. Since we have not used early stopping, so this will take some time because it will run for 30 epochs. So I am going to fast forward in time. So the model has trained and we are getting accuracy of 85%, which is 6% point jump from the previous model, which is a good thing for us. Next, we visualize the losses and accuracy. So this model is much better than the previous models. Why? Because we are getting almost same accuracy on training and validation data. That means we can safely say that our model is going to give 85% accuracy on unseen data. And this can be concluded through graph because the training accuracy and the validation accuracy curve are close to each other, which suggests that we have almost same accuracy on both the data. Now I would encourage you to try different configuration for this model. First try to increase the number of filter and then go with the layers. So that's all for this video, and if you are new to my YouTube channel, please do like and subscribe and press the bell icon for the future update. So see you in the next video. Till then, bye, wear mask, stay safe.